Okay, so good morning, everybody. Welcome to this section of solutions to these exercises. All right, so here we have the module 5. Okay, so I will be trying as much as possible to see how far we can go to finish this module in this session. Okay, so we begin the question 5a. Question 5a. Or should I go back to my black? I think so. Yeah. Okay, so let's come back here. Okay, so the 5a says the I part of it, find the standard matrix find the standard matrix, but this one I may not be writing all the questions, as suppose. So you will permit me, associated with the transformation any dim that phone associated with the transformation, and here is the transformation t of x1, x2, and then x3 to x4 is equal to, they said, x1 plus x2, and then x2 plus x3, and then x3 plus x4, and then 0. Okay, so this is a linear transformation from, you can clearly see that is going from R4 to R4, so it's transforming this vector and then it's producing another vector of 4 dimension also. The vector is transforming is a 4-dimensional vector and it's producing a 4-dimensional vector as well. So it's going from R1 to it's going from R4 to R4. Okay, so here they asked us to get the linear transformation, the standard matrix for that transformation. Okay, so it's a very simple thing to do. First of all, is to observe that what you have here is are just of course vectors. Okay, sorry, or you can just say equations, right? So, and once you observe that, then all you need to do is just to extract the coefficients just as we used to do. So your matrix A is simply going to be the matrix. Here you will extract 1, 1, and now if you watch all the equations or the expressions, you will discover that the first one was x1 and x2, but the second one continued to x3, the third one continued to x4, meaning that all of the equations actually have from x1 to x4. The only difference is that in the first equation, the coefficient of x3 is 0 and that of x4 is 0. And when you come to the second equation, the coefficient of x1 is 0, x2 is 1, x3 is 1, x4 is 0. And then for the third equation, x1 is 0, x2 is 0, then 1, 1. And the last one, you have zeros all through. Okay? And that is your standard matrix for, and then the answer for AI. Okay, so we go over to the second question there. It says find the linear transformation. Okay, so we are to find the linear transformation T that moved from, okay, so sorry, for the linear transformation, not find. Okay, so there is a linear transformation from from TR3. This one also moved from TR3 to TR3. Okay, so meanwhile, this module is more of linear transformations, rank and kernel of linear transformations, rank and nullity of transformations, basis for the range of transformations, and all of that. They mentioned that under the introduction of the exercises. Okay, so you should know where we are focused on. All right, so let's go on now. So we are given that the second one is a linear transformation from R3 to R3. Okay, and then we are okay. So and then we are given the definition. So is defined by the equations, just like the up one was defined by equations. Okay, so here are the equations. You have that 3x1 plus 5x2 where is it, minus x3 is equal to b1. Then the second one is 4x1 minus x2 plus x3 is equal to b2. And then the third one is 3x1 plus 2x2 then minus x3 is equal to b3. Okay, and okay, so these are the three equations. So now remember that this transformation means that it is moving from R3 to R3. That means it will act on a vector that has 3 components to produce another vector of 3 components. Okay, and so let's look at the question. So the question says we should find the standard matrix. Okay, so just like what I did up there, so your standard matrix, you can call it A or anything. You can choose, okay, in fact, let's call it another variable. Maybe we should use let's say B this time around. Okay, so our B is going to be equal to, just pick out the coefficients of the main matrix without touching the constant part. You know, if you touch the constant part, you already have what we called the augmented matrix. So you're looking for the standard matrix. So just pick the coefficients: 3, 5, minus 1, 4, minus 1, 1, then 3, 2, minus 1. Okay, so these are the matrices or the entries that will make up the standard matrix. Okay, and then that's not all the question. They said after the standard matrix we should then find maybe let me use this for here. So the second one said we should find T of minus 1, 2, and 4. Okay, so first of all, if I have T of let's say x, y, z, what does it mean? Remember that your T is acting on x1, x2, x3 and all that. So, and you can clearly see what that means. So because if you watch from here, you will see that the coefficients of all of these x1, x2, x3 are what we have here. So it means that whenever T acts on a matrix, which we can represent as x1, x2, x3, not a matrix, a vector. So when it acts on a vector, it simply multiplies the standard matrix with the vector in a column form, and then gives you the value of the constants. Okay, so if you watch here, you discover that by the time you do this multiplication, you will get back the equation we have up there. So the implication is that, let me show us. So the implication is that if our T acts on any vector like this, that it is actually the same thing as having the standard matrix, in this case is B, multiplied by the column vector of that your what do you call it, that your vector that your t is acting on, so which is x1 to x3. So by the time you multiply this, it should be equal to the constant part. Okay, maybe I should have used another what do you call it, another variable here, since our constant parts are b's. So maybe I should have used q here. Okay, so that means this would be equal to q times x. Okay, so should now be equal to b. So that's actually what the definition of this linear transformation does. Okay, so by implication, that means we know what to do here already. And what are we going to do? So this is equal to q. Excuse me. So what that means is that our t of this is actually equal to t of minus 1, sorry, q times minus 1 times 2 times 4. That's all. So by the time you perform this multiplication, that's going to give you, yeah, good morning Daniel, how are you? Okay, so that's going to give you exactly what you needed. All right, so let's go ahead and do that. So let me remove this. So that means I will need to go down a little bit. Okay, so what's my q now? My q is 3 5 minus 1 4 minus 1 1, then 3 2 minus 1. Okay, so you are multiplying this with minus 1 2 and 4. All right, let's try to do that now. So in doing this, we are simply going to have, you know how we do matrix multiplication. So this is going to be, the first row will multiply, so it's just going to be a 1 column matrix. So if this multiplies this, you're going to have 3 times this is minus 3 plus 10, then plus minus 4. The second one will be this times this, which is minus 4, then minus 2, and then plus 4. And then the last one is going to be minus 3 plus 4, then minus 4. Okay, so by the time you multiply that, it's simply going to give you, by the time you add all that you have, you are going to get 3 here, then you will get minus 2 here, and then the last one should be minus 3, because of course this will cancel this and this will cancel this. Okay, so and this is the value of your t of minus 1 2 and 4. All right, so and that's the solution for the second one. Okay, so we look at the third one, okay, which is already the b. Okay, so b says that we are given that t, a linear transformation, is going from R2 this time around to R3. So it's transforming 2-dimensional vectors to 3-dimensional vectors, and then is defined this way: t acting on any x1 x2 is equal to the following. Okay, so we are given x1 plus 2 x2, and then the second one minus x1 minus 3x2, and then the third one, okay, and then the third one is the third one is where is it again? Minus 3x1, and then minus 2x2. Okay, So these are the values you will get when T acts on any vector, any two-dimensional vectors. So the question now says that we should find x such that T of x is equal to minus 4, 7, and 0. Permit me to let you know that whenever we write x in this way, which I have said before in one of the solutions. Yeah, Rita, good morning. Which number am I solving? Module 5. I started from module 5, Rita. You know we have concluded module 4 since. So we are starting with module 5. Okay, so see it here. I started from module 5. Number what exactly? Question 1. Oh, sorry. I just mentioned A. Sorry. It's question 1. Okay. So it's question 1 of module 5. And then question, we are beginning with A. So we started with AI. And then we had AII. And then we have gone over to B now. Okay. I hope you got that question, Rita. Good morning. How are you? Okay. So, all right, let's move on. So from here now, okay, now what this question is saying, like I was trying to explain, is that when you are giving x in this form, you should know that it's, Rita, you're welcome. You should know that it's a vector we are referring to. So because your t is acting on a vector, so this x actually is like x equal to x1 comma x2. So you're looking for the values of x1 and x2 such that it will produce this. So what vector of 2 dimension will this particular linear transformation act on to get this particular one? That's what this question is saying. Okay, so and all you need to do is to formulate the equation. So solution. So like what I just said now, we are looking for t of x1, then x2, that will be equal to minus 470. And remember how that's going to be. So whenever your, what do you call it? Whenever your vector now acts on this, of course, what it's going to do is to multiply by the standard matrix that you form with this, and then it should give you equal to this. So what that is saying is that I should produce my standard vector. So, standard matrix. Of course, a matrix is a vector. Okay, so standard matrix, let me still call it A here now. So our standard matrix will be equal to, remember here you have only 2x. Okay, so it's going to be only 2 coefficients here, 1 and 2. The next one minus 1 and minus 3. The next one minus 3 and minus 2. Okay, so meanwhile I think doing this at this time is actually beautiful, so that people will not okay, so you'd have to be very, very committed to be able to write this one. So I think that will make the difference. Yeah, Miracle, I'm seeing your comment on the, who again? Rita. Okay. So, like I was saying, so this is our standard matrix. So the implication is that this particular t act, when it acts on this, that it should be equal to this. So which implies that that standard matrix, or let me just put A multiplied by I shouldn't have used that big bracket. A multiplied by x1 x2 is equal to minus 4, 7 and 0. So that's the meaning of that. Okay, and we can quickly now interpret this by producing our different equations. So which is going, let me still write on this side because of space, which means that our A, which is equal to 1, 2, minus 1, minus 3, minus this blah, that is going to multiply with our x1 and x2 to give us minus 4, 7, and 0. Okay, so let's try to produce that equation. Remember, you can solve this from this place. Just attach your coefficient matrix to it. We have been doing that. In fact, let's use that approach. So if we bring in our the constant part, so we have 1, 2, minus 4, minus 1, minus 3, and then 7, then minus 3, minus 2, and 0. So no need of producing the equations. We can get that from here, and then after we've reduced, we can now produce the equation. So you can clearly see that you can transform sorry about that, excuse me. Yeah. Okay, so you can transform this to give us, of course, this becomes our pivot, and then we can get our second row by doing R2 plus R1. Their size is equal, signs are opposite, so you add. That meanwhile, our row 1 will be the same. So our row 2 now is going to be 0. This one will be minus 1. This one will be 3. Then the second, last one, if you eliminate, you are going to have row 3 plus, because the signs are still opposite. So 3 times row 1. And that's going to give us, okay, so there you are going to have 0 here. All right, 3 times this is 6, plus this will be 4. 3 times this is minus 12, plus this is still minus 12. Okay, all right, so okay, so from these last two equations, you already, or last two rows, you already have equations to solve. So you just substitute back your x values. So here you are going to have x1 plus 2x2 is equal to minus 4. Second one, minus x2 is equal to 3. Okay, and it's enough. If you bring this, it will still give you the same value of this. I hope you know. Okay, so from there, you are going to get that our x2 is equal to minus 3. So even if you put x2 here, you are still going to get 4x2 is equal to minus 12. And if you divide, you still get x2 as minus 3. So only these two equations are enough. And then to get our x1, just substitute here as minus 3, and that's going to be 2 times minus 3, which is minus 6, is equal to minus 4. Therefore, our x1 is minus 4 plus 6, which is 2. Okay, so I can summarize here. x1 is 2 and x2 is minus 3. Therefore, we can now say that the x that we are looking for is actually x equal to 2 comma minus 3. You can either write it as a column vector or as a row vector. The solution is just the same. Okay, so and that is for B. Okay, so we go straight away to question C. And C says we should find the standard matrix A for the transformation. Look at the transformation there. T of x equal to 3x. Okay, so T of x equal to 3x. I'm going to be, that's, okay, let me write it. Equal to 3x. I'm seeing a space there. So we do not know whether, okay, where x is from R3. Sorry, R2. So this x here is from R2. So we do not know whether this is, if you watch in that material, you see that there's a space there. So we do not know whether this is x, 3 and then x, that's differently, or it's actually 3x. Okay, so let's see what that is going to look like. So in other words, they are saying that our x is from R2, so meaning that there is a transformation from where is it? So there's a transformation from what do you call it? From R2 to R1. So it's just giving us only one entry. Okay, so you can see only one entry, 3x. That's if we treat that as 3x, assuming we of course take it that there is no space between that 3 and x. Okay, so that means it's transforming vectors from R2 to R1, giving you only one entry. Okay, so what that means is that we can from here get our standard matrix, which is matrix, okay. Watch what is going to happen there. From this particular equation, you will see that our matrix, we can use P again here instead of A. Like I said, you must not use A. So remember we said you just bring out the coefficients. So assuming it was, let's say, 3x plus or 3x1 plus maybe x2. So you are going to bring out 3 and 1. That means it is only a row matrix. So, but then here, a row vector. So, but here you just have only one entry. So just bring out that single coefficient there. So your standard matrix is equal to 3. But then you can actually produce it because remember that if you have that you're transforming into from R2 into R1. So what is what the implication is that you are going to be having your T acting on a matrix that is from at least 2 dimension. That's maybe 2 by 2. Okay, so and what it means is that this thing is actually a constant matrix, diagonal constant matrix. So which you can now remember I told you that if we give you a matrix and we say that A is equal to matrix 1, that one all you need to ask is what is the dimension of A. So of course it's going to be, once you begin to have constant matrices, it's going to be a square matrix. So if it is a 2 by 2, that one means 1 0 0 1. If it's a 3 by 3, that one means 1 0 0 0 1 0 and then 0 0 1. Okay, so depending. All right, so since we are working on a 2-dimensional matrix now, so the implication is that this 3 is actually 3 0 and 0 3. Okay, so and that is the standard matrix that we are looking for there. So it's actually the same thing as let me put it this way. So it's actually the same thing as 3 times I. So, and this I is coming from 2-dimensional I. So you can call it I2. Okay, so this 3 is multiplying I2 and it is equal to this. Alright, and that is the standard matrix that is required from you there. Okay, so by implication, it means that this thing is not supposed to be only 3x. It should actually be 3 and then x the other way. But then let's go on. Okay, so let's see. And then the next question says that we should find, okay, meanwhile this is, okay, that's all. So that's, we go to D. I thought that there were 2 questions in C. So this is find the standard matrix for the transformation. Okay, I'm reading C again. This says we should find T of x given that given that this one is equal to 1, 2, 3, 4, and that our x is equal to, and that our x is equal to 3 and minus 2. Okay, so we are asked to find t of x. All right, so let's see. Okay, so ordinarily this is just telling you that the standard matrix of this is given as this, or okay, and that's the standard matrix of the linear transformation is given as this, and you're asked to find t of x if x is equal to that. Okay, so all you just need to note is what I explained now, that your t, that's this coordinate of t, actually means is given as this. That is actually the same thing as your standard matrix, so we don't necessarily have to use this. Okay, so you can just start with our t of x. Remember I said that our t of x is the same thing as a times your x. That's the standard matrix. Let me put it that way. Standard matrix times x. Okay, so and in this case our standard matrix, which is given there as our coordinate of t, is 1, 2, 3, 4, and so it's multiplying our x. And what's our x? Our x is 3 and minus 2. Okay, so once you multiply out this, that is what you are looking for. Okay, so and you are done. So quickly let's do that. So 2 going into that. Okay, Rita is saying, sir, I thought the 3 row should be reduced. Is it the 3 row or the 3rd row? Which question are you referring to? I suppose you're referring to the where I did a row reduction. Look at it here now. What else are you reducing to? Do you want to reduce to this one? This is just, remember you usually put a demarcation here. Rita, I hope you would see this. Okay, so you usually put a demarcation here. Your reduction actually ends here on your A. You don't get into your B. That's the constant part in doing your reduction. So you only reduce on your A. We have already reduced it. There's nothing else to reduce here. Okay, so this is the last this thing here. All right, if you reduce this, that means you're turning a variable to 0. Okay, so you don't turn a variable to 0. So you keep going until you have gone this way. So since this, of course, this is on a variable, so you don't turn these last ones to 0. Assuming there is another maybe column, then you can reduce this. I hope you get what I'm saying. All right, so that's that. Okay, so back to what we were saying here. If we do this multiplication, we'll have 2 and 1 multiplying this. That will be 3 minus 4. While this one will be 9 minus 8, which is equal to minus 1 and then 1. Okay, so this is the value of your t of x. Yeah, Rita, you're welcome. Okay, so that's your t of x as required. And this happens to be the end of question 1. So that's the end of question 1. And then we would have to enter into question 2. Okay, so can I go? Can I continue? All right. Okay, so let's go to the next one. Okay, so question 2. We are asked to determine with good reason if the linear operators that are defined by the following equations, if the linear operators that are defined by the following equations are 1 to 1, okay. All right, so let's go. The first one, the equations given are w1 equal to 2x1 minus 3x2 and w2 equal to 5x1 then plus x2. Okay, so there is a hint there. They said are A columns linearly independent, or is A invertible? Okay, so I'm the one bringing in that second statement. Okay, so okay, so that's what you need to check. If you are able to check any of that, then you will confirm whether they are 1 to 1 or they are not 1 to 1. All right, so meanwhile, when we come to 1 to 1, we did that in Maths 102. That's where we talked about every entry being mapped to a unique image. Okay, so let's see that. So what do you need to do here is very straightforward. Just bring out your standard matrix for each of them. Okay, anyway, I'm doing I differently. So if we bring out the standard matrix, which is 2 minus 3, 5 and 1, okay, so you just check if they are linearly independent or if they are invertible. Okay, so I think invertibility will be much easier to check for a 2 by 2. So let's check the invertibility. And how do you check that? You just you know how to check whether something is invertible. Just check the determinant. If the determinant is 0, then it is invertible. But if the determinant is not 0, then it is not invertible. So let's look at that. How do you get the determinant? So assuming that I called this A, so the determinant of A is simply equal to this times this, which is 2, minus this times this one, which is minus 15. And of course, you can see that this is not equal to 0. And since this is not 0, then we can say since A is invertible, then it's enough to conclude that the linear operator in I, the linear operator is a 1 to 1. Is 1 to 1. Okay, all right, and then you can now go ahead and do that of II. Maybe I will leave you to be doing some things. Remember, I said either you check invertible or you also check linearly independent, or you check the both. Okay, so but one should be enough. All right, that's what the hint tells us. So that's column linearly independent. Actually, that means you perform a row reduction and ensure that each column has a pivot. Okay, so once each column has a pivot, then it is linearly independent. Okay, should we try that of B? Okay, or I let's go. Let's do it together. Okay, so in that one, your A, which is the standard matrix, is going to be equal to, okay, I did not even write out our our equations there. So the equations there are I have a little of cold. Sorry about that. Just that I needed to do this. If not, I would have not bothered. Okay, so this is plus 3x3. W2 equal to 2x1 plus 5x2 plus 3x3. And then W3 is equal to x1 plus 8x3. Okay, so and that's going to give us, okay, so if we produce the matrix here, we can call it B. So that's going to be 1, 2, 3, 2, 5, 3, and then 1, 0, 3. Okay, so 0, 8. Okay, so we can try to see if we will reduce this and then see if it is going to give us, okay, this looks like the end of this board. Okay, so let's attempt that here. Okay, so okay, so we can first of all do for the first column. If we do that, you're going to get your first row will remain the same. Okay, so the second row they are the same sign, so you subtract. You just have R2 minus 2R1. So if you do that, this will be 0. 2 times this is 4. 5 minus 4 is 1. 2 times this is 6. 3 minus 6 is minus 3. And then if you do this one, they are equal. Just subtract R3 minus R1. That's all. So you have 0 here. This minus this is minus 2. And then, where is it? 8 minus 3 is 5. Alright, so we reduce again. This time around, R1 and R2 will remain the same. Okay, you have 2, 3, then 0, 1, minus 3. Okay, so what will now be our row 3? You want to eliminate here. So there you will have R3 plus, since the signs are different, 2 times R2, because this is now our pivot. So this is going to give us 0. Now this plus 2 times this will be 0 as well. And then this plus 2 times this. 2 times this is minus 6. So if you add it, you get minus 1. Okay, so you are done. You can clearly see that the columns are linearly independent because every column has a pivot. Every column has a pivot. And so they are linearly independent. Yeah, Chidera, thank you. Andy, thank you also. Okay, so they are linearly independent. And once you conclude that they are linearly independent, so it's enough to say also that this implies that the linear operator in II, sorry, this thing is II, not B. I wrote B here. Okay, so the linear operator in II is also 1-to-1. Is also 1-to-1. I'm writing this way so you can complete it in words. So it's also 1-to-1. All right. So and that is for question A. Okay. So and then we move over to question B, and you will permit me now to go to a new page. I hope you have gotten all that is in this page now. Okay. So here we now have. Okay. Let me reduce this. Okay. Or maybe one more. Okay, so here we have question B now. And B says, where is it? That let V1, V2, V3, let V1, V2, V3 be vectors in V. Okay, so these are vectors in vector space V. And see a linear transformation from that V vector space to R3. So it's picking elements, it will act on elements of V and then give you something in R3. Remember, we've not been told the dimension of V yet, so we don't know the number of entries that will be in each of these V. Okay, so it says it's a linear transformation defined as follows. So look at the definition. T acted on V1 and gave us 1, -1, and 2. The same T acted on V2 and gave us 0, 3, and 2. Remember that what, like I said before, what you have at the end here tells you the number of entry you will get in the vector that the T will produce when it acts on anything. So that's why we are having 1, 2, 3 entries in all of these vectors. So because the T is going to R3. Okay, so I just needed you to note that again. So when it acts on V3, you should also expect to get a 3 entry or 3 dimensional vector. And then they gave us -3 and they gave us 1 and 2. Okay, so the question now says find, sorry about that. So the question says find I'm coming. Okay, so meanwhile, my main channel, you know, this is my second channel. My main channel got to 1 million views some days ago. So I know some of you are not on that channel. I know. Go and subscribe to that channel. That's my name, Precious Ugweze. You should also share this one to friends. It is very shocking that by this time we are still around 600 subscribers on this channel after all of the things that we have been sharing here. So you should share this channel, and if you use the materials here, the only right thing to do is to subscribe, like, comment, appreciate what is being given to you. Okay, so I expect that by the end of this day that we should have over 1,000 subscribers on this channel. It's very important. Okay, meanwhile, celebrate with us on Precious Ugweze. That's Maths Experience. You can go there and give a shout out to us. Of course, I think I'm going to be making a post on the post section of that achievement. It's not an easy one. Okay, so they said we should find T of 2v1 minus 3v2 then plus 4v2. Okay, so meanwhile, this is a linear combination of v1, v2, and v3. Okay, so what is that going to be? All right, so first thing first is to know that this is a linear transformation. And what is the implication? What does it mean for it to be a linear transformation? It means that it can do what we call a scalar multiplication and distributivity. Okay, so it can distribute on a linear combination. Let me show you what that means. Remember that if I give you something like a times x plus y, you know that you can actually open this bracket and you get ax plus ay. So the reason is because the function you have in the bracket is a linear function, and so you are allowed to enter into this, to perform a scalar multiplication. So every linear transformation can do scalar multiplication and all of those additions and all those things. So what I just said now, what it means is that my T of 2v1 minus 3v2 plus 4v2 is actually the same thing as opening this bracket and allowing your T to come into here. So if it comes on this, it's actually the same thing as T of 2v1 minus T of 3v2 plus t of 4v2. So you can do scalar multiplication with your linear transformation. Okay, and if that is true, you can, this one now is a linear combination, so you can also do scalar multiplication, meaning I can bring out these coefficients inside here out, so I can have something like 2. These 2 can come out and I'll just have 2tv1 minus this 3 can come out and I'll have 3tv2, and finally this 4 can come out and I'll have 4tv2. Sorry, the last one is t3 sorry, v3 I beg, that is v3 and not v2. Okay, so and you are done. The reason you needed to do this is because you already have a value for t of v1, t of v2, and t of v3. So all you need to do now is to perform a substitution. Alright, so I am going to come here now and then substitute my t of v1, and what is that? 1 minus 1, 2, minus 3 times my t of v2, 0, 3, and 2, and finally plus 4 times my t of v3, which is minus 3, 1, and 2. And that is it. So what is our solution? Should I jump this one step? Okay, let me pity you. So open the brackets, you have 2 minus 2 and 4. Open this one, you have 0, 9, and 6. Open the other one, you have minus 12, 4, and 8. And then finally, you will just add to get 2 minus 0 is 2, plus minus 12. That will be 2 minus 12, which is minus 10. Then minus 2 minus 9 is minus 11. Am I correct? And then plus 4 is minus 7. And finally, 4 minus 6 is minus 2 plus 8 is 6. And you are done. That is the solution to that question B. Okay. Amara, you're welcome. Good morning. Daniel, thank you for that. Thank you. Funanya, you're welcome. Okay. So, and so we are done with question B. We are moving over to question, C. See me now, I'm writing B again. Okay, so let me try to reduce this so that you can be seeing it while we go over to C. Okay. So C says, where is it? That we are letting t of x1, x2 to be equal to 3x1 plus x2, comma, 5x1 plus 7x2, then x1 plus 3x2. Okay, so that is the linear transformation. And then he's saying we should show that t is 1 to 1. And then B, does t map R2 onto R3? Of course, we are going to confirm that. But then that's exactly what we are seeing here. You don't even need to check. Because the solution or the value you are getting after t is acting on 2 entries, and the value you're getting are 3 entries. So it's moving from R2 to R3. That's obvious. Okay, so but we will look at that later. Okay, so solution, we are to the I part. We are to check if t is 1 to 1. Is t 1 to 1? Okay, that's what we want to check. Remember what we said? You should bring out the standard matrix, and we have been using A and B and P and all that. So if we bring out the standard matrix, just the coefficients 3 and 1, 5 and 7, 1 and 3. Okay, so we are to check if this is linearly independent on the column. Okay, so remember there was an approach we used from the beginning of these solutions, where they were asking us about linear independence and linear independence. There we use the approach of checking if they are multiples of each other, especially when you have only two columns. So you can see we just have two columns here. Is this column a multiple of this one? Is there any how you can multiply this to get this? You will see that obviously it's not possible. This is not a multiple of this, and so you don't necessarily need to check if each column will have a pivot. And in any case, it will have a pivot. By the time you reduce this to 0, there will be a pivot here, so it will stay. But then we can just use that approach of multiples. So you can clearly see that column 2, okay, let's say since column 2, let's put it that way, since column 2 or column 1 and 2 are not, since column 1 and 2 are not multiples of each other, then T is 1 to 1. Okay, so meanwhile, you can, another person may choose to use the linearly independent, of course that's reducing this to zeros. You can transform this to zeros and check if this guy will remain. Once that guy remains, then it means there is a pivot here and there is a pivot here. Remains, I mean, if it doesn't turn to 0. Okay, and of course it won't. So if you check it, in fact, let's do that. The first row will be 3 1. To eliminate this, you can do R2 3 times R2 minus 5 times this, and of course that will give us 0. 3 times this will be 21 minus 5, that is 16. Okay, so already you see we don't have 0 here. So no matter what this one will become, since we don't have 0 here, after transforming this to 0, then it means that this one also has a pivot. So it's good enough to stop there. So you may use that approach if you want. Okay, so but we have confirmed that the transformation is a 1-to-1 transformation. And then the second question there says it says, meanwhile the material gave a hint, we should check if ax equal to 0 has only the trivial solution. And of course it's true. Meanwhile, we should maybe finish this. If you finish this, anyway, I hope you know you could have changed these two rows. That's row 3 to become row 1 and row 1 to become row 3. So, but remember, like I usually say, it doesn't really matter. So here we can also now reduce this, which will be this 3 of this minus this. So 3 of this is 3 minus this will be 0. 3 of this is 9 minus this will be 8. Okay, so you can clearly see that, of course, whatever is what you have here, if you equate it, you will get a value for x2, and then from there you will get a value for x1. And if this is equated to 0, like that hint is saying, if you equate here to 0, then you are going to get, of course 8x2 equal to 0 will give you x2 as 0. 16x2 equal to 0 will still give you x2 as 0. And if you substitute here, you still get x1 to be 0. So all your entries will be your x1 and x2 will be 0 when you equate the equation to 0. That means your solution is trivial. All right, so they said that's another way to check for 1-to-1, and of course you are correct. Okay, so now for the second part, remember I said we are going to consider other other conditions before concluding whether it is a transformation. Let me write out that question. So it says, does T map R2 to R3 onto R3? Okay, does it map onto R3? Okay, that's what they're asking us. Okay, so okay, all right, so you can clearly see what the question is trying to do there. It's trying to check if you understand what we have been doing. Now remember that you look at our A, the standard matrix here. So you can see that our standard matrix has only 2 rows. Okay, so and if it has only 2 rows or 2 entries on the rows, that means it cannot multiply. Look at it. Since our A is equal to 3, 1, 5, 7, 1, and 3, so it cannot multiply an x that will have 3x values. Okay, this multiplication cannot hold, because for this multiplication to hold, your rows must have the same number of entries as the column of this before they can multiply to give you an equation. So 3 will multiply with x1, 1 will multiply with x2, so what then should multiply with x3? Okay, so you can see that linear this thing will not work. So that means it is not taking is not mapping R2 to R3. That mapping is not going to be possible. Okay, so you can just conclude that since our A has 2 entries in the rows, since A has 2 entries in the rows, has only 2 entries, 2 entries in the rows, then and the columns of our x, the column of the x in the R3 which is supposed to go to. Remember, if it is mapping it onto R3, that means your x values, the one that should multiply with your A, should be coming from R3. So the x in your R3 are of 3 dimensions, all right, and the column of your x are in R3. So it means the multiplication cannot work. So thus you can conclude that the linear transformation does not or cannot allow or cannot map, anyone cannot map R2 onto R3. So this particular linear transformation can only map R2 to R2. Okay, because the rows are 2 entries, so it can only map onto R2. So but you can see that from the first point when we saw this, you see that we had seen 3 entries here, so it was looking like it was obvious. So and that's why you need to check all the possibilities to be able to conclude that something will work or not. Okay, so and that is for C. Then we have the next one, which is question D. And okay, let me come down a little bit. And our D says that we should do what? Consider the problem of determining whether the system is consistent. Okay, so I think in class I started showing you people how to check consistency of an equation or a system. So a system is consistent if it has a solution. Okay, so we are given that, and then the next one we have minus 6x1 plus 3x2 minus 7x3 equal to 5. So they said we should check if this system is consistent. Okay. I'm trying to check if the question has any link with the previous things we have been doing. Okay, so it doesn't. Okay, so to check if this has a solution, all you need to do is just remember, like I said, is to check if there is a solution. And so just get out the associated matrix. It can be the the augmented one, or even the normal one. Okay, so what's the associated matrix? You can call it A is equal to 3 minus 1 2 1 if you want. That's if you want to make it augmented. And then the next one is minus 6 3 minus 7 5. So if we make it augmented, remember to put your dotted lines there, but we may choose not to, okay, because it doesn't really matter. Okay, so let's leave it that way. Okay, so we try to reduce, of course, to echelon form by deleting this. All right, and that's going to give us equation 1, or row 1 will remain the same. So what will be our row 2 now? Our row 2 will now be from the algorithm. So your row 2, if you multiply this by 2, two of them will be equal. So let's multiply it by 2. And so two of them are of opposite signs, so you add. Okay, so 2 times this is 6 plus minus 6 will be 0. Then come here, 2 times this is minus 2. You add it here, you get 1. This times 2 is 4. You add it to there, you get minus 4. Okay, so of course you are done with the reduction. This is already a pivot. You have a pivot here, you have a pivot. But that's not what you need to get what you want. Now, what is it? The last thing we did in the class, we were trying to check the nature of solutions. So, and we said that for a system to have a solution, the associated matrix, meanwhile, we said there are 3 types of solutions, that you have unique solution. Okay, and we said for a unique solution, the number of equations must be equal to the number of variables. So here the number of equations is not equal to the number of variables. So it means in that case, remember we said that one is for many solutions. Okay, so for many solutions, your n should be less than your r. And then finally, we said for no solution at all, that there should be an inconsistent equation. That means there should be an equation that is not true. And you can see here, there is no equation here that is not true. Okay, so, and we said that for an equation to be untrue, it means you are going to get something like 0 equal to a number, maybe 10. And you know that 0 cannot be equal to 10, so you say that equation is not true. So, but in all of this, what we just have is that it satisfies the second condition. Okay, and so it has many solutions. And since it has many solutions, you can therefore conclude that therefore the system is consistent. The system is consistent. So that's the conclusion there. All right, and then okay, then it says define an appropriate A and an appropriate linear transformation and restate the problem in terms of linear transformation. Okay, so let's go. Okay, let me try to reduce so that we can still be seeing what we have. Okay, so now here they are asking us to get the linear transformation that will produce this. Okay, that's what the question is saying. All right. Okay, so how do you handle that? Okay, so I'm going to be giving you exercise here. You know, I've always been trying to give you things that will make things different. Okay, at least you will struggle with one or two. Okay, so but I'll give you a hint. Okay, and the hint is that this is our standard A, and then the B part is equal to 1 and 5. Okay, so all you need to do is to determine, first of all, to determine whether your B is in the range of your A. Okay, so you first of all check all of that and see what that is going to give you. I will allow you to struggle with this. Should I lead you through this? No, I will leave it. Chidera, sir, I think that -4 is supposed to be the algorithm. Suppose